In the last video, I talked about how when faced with a machine learning problem, there are often lots of different ideas for how to improve the algorithm. In this video, I'd like to talk about the concept of error analysis, which will hopefully give you a way to more systematically make some of these decisions. If you're starting work on a machine learning problem or building a machine learning application, it's often considered very good practice to start not by building a very complicated system with lots of complex features and so on, but to instead start by building a very simple algorithm that you can implement quickly. And when I start with a learning problem, what I usually do is spend at most one day, like literally at most 24 hours, to try to get something really quick and dirty, frankly not at all a sophisticated system, but get something really quick and dirty running and implement it and then test it on my cross-validation data. Once you've done that, you can then plot learning curves. This was what we talked about in the previous set of videos, but plot learning curves of the training and test errors to try to figure out if your learning algorithm may be suffering from high bias or high variance or something else, and use that to try to decide if having more data, more features, and so on are likely to help. And the reason that this is a good approach is often when you're just starting out on a learning problem, there's really no way to tell in advance whether you need more complex features or whether you need more data or something else, and it's just very hard to tell in advance. That is, in the absence of evidence, in the absence of seeing a learning curve, it's just incredibly difficult to figure out where you should be spending your time. And it's often by implementing even a very, very quick and dirty implementation and by plotting learning curves that helps you make these decisions. So if you like, you can think of this as a way of avoiding what's sometimes called premature optimization in computer programming. And this is an idea that just says that we should let evidence guide our decisions on where to spend our time rather than use gut feeling, which is often wrong. In addition to plotting learning curves, one other thing that's often very useful to do is what's called error analysis. And what I mean by that is that when building, say, a spam classifier, I will often look at my cross-validation set and manually look at the emails that my algorithm is making errors on. So look at the spam emails and non-spam emails that the algorithm is misclassifying, and see if you can spot any systematic patterns in what type of examples it is misclassifying. And often by doing that, this is the process that will inspire you to design new features, or they'll tell you what are the current things or current shortcomings of the system and give you the inspiration you need to come up with improvements to it. Concretely, here's a specific example. Let's say you've built a spam classifier and you have 500 examples in your cross-validation set, and let's say in this example that the algorithm has a very high error rate and it misclassifies 100 of these cross-validation examples. So what I do is manually examine these 100 errors and manually categorize them based on things like what type of email it is and what cues or what features you think might have helped the algorithm classify them correctly. So specifically by what type of email it is, if I look through these 100 errors, I might find that maybe the most common types of spam emails it misclassifies are maybe emails on pharma or on pharmacies, basically emails trying to sell drugs, maybe emails that are trying to sell replicas, so sort of fake watches, fake random things, maybe have some emails trying to steal passwords. These are also called phishing emails, but that's another big category of emails, and maybe other categories. So in terms of classify what type of email it is, I would actually go through and count up, of my 100 emails, maybe I find that 12 of them mislabeled emails are pharma emails, and maybe 4 of them are emails trying to sell replicas, like sell fake watches or something. And maybe I find that 53 of them are these what's called phishing emails, basically emails trying to persuade you to give them your password, and 31 emails are other types of emails. And it's by counting up the number of emails in these different categories that you might discover, for example, that the algorithm is doing really particularly poorly on emails trying to steal passwords, and that might suggest that it might be worth your effort to look more carefully at that type of email and see if you can come up with better features to categorize them correctly. And also what I might do is look at what cues or what features, additional features might have helped the algorithm classify the emails. So let's say that some of our hypotheses about things or features that might help us classify emails better are trying to detect deliberate misspellings versus unusual email routing versus unusual, spammy punctuation, such as if people use a lot of exclamation marks. And once again, I would manually go through and let's say I find 5 cases of this and 16 of this and 32 of this and a bunch of other types of emails as well. And if this is what you get on your cross-validation set, then it really tells you that maybe deliberate spellings is a sufficiently rare phenomenon that maybe is not worth a lot of time trying to write algorithms to detect that. But if you find a lot of spammers are using, unusual punctuation, then maybe that's a strong sign that it might actually be worth your while to spend the time to develop more sophisticated features based on the punctuation. So this sort of error analysis, which is really the process of manually examining the mistakes that the algorithm makes, can often help guide you to the most fruitful avenues to pursue. And this also explains why I often recommend implementing a quick and dirty implementation of an algorithm. What we really want to do is figure out what are the most difficult examples for an algorithm to classify. And very often, for different algorithms, for different learning algorithms, they'll often find similar categories of examples difficult. And by having a quick and dirty implementation, that's often a quick way to let you identify some errors and quickly identify what are the hard examples so that you can focus your efforts on those. Lastly, when developing learning algorithms, one other useful tip is to make sure that you have a numerical evaluation of your learning algorithm. And what I mean by that is that if you're developing a learning algorithm, it's often incredibly helpful if you have a way of evaluating your learning algorithm that just gives you back a single row number, maybe accuracy, maybe error, but a single row number that tells you how well your learning algorithm is doing. I'll talk more about this specific concept in later videos, but here's a specific example. Let's say we're trying to decide whether or not we should treat words like discount, discounts, discounted, discounting as the same word. So, maybe one way to do that is to just look at the first few characters in a word. Like, if you just look at the first few characters of a word, then you figure out that maybe all of these words have similar meanings. In natural language processing, the way that this is done is actually using a type of software called stemming software. If you ever want to do this yourself, search on a web search engine for the Porter stemmer, and that would be one reasonable piece of software for doing this sort of stemming, which will let you treat all of these words, discount, discounts, and so on, as the same word. But using a stemming software that basically looks at the first few alphabets of a word, more or less, it can help and it can hurt. And it can hurt because, for example, the software may mistake the words universe and university as being the same thing because these two words start off with very similar with the same alphabets. So if you're trying to decide whether or not to use stemming software for a spam classifier, it's not always easy to tell, and in particular, error analysis may not actually be helpful for deciding if this sort of stemming idea is a good idea. Instead, the best way to figure out if using stemming software is going to help your classifier is if you have a way to very quickly just try it and see if it works. And in order to do this, having a way to numerically evaluate your algorithm is going to be very helpful. Concretely, maybe the most natural thing to do is to look at the cross-validation error of the algorithm's performance with and without stemming. So if you run your algorithm without stemming and you end up with, let's say, 5% classification error, and you rerun it and you end up with, let's say, 3% classification error, then this decrease in error very quickly allows you to decide that, looks like using stemming is a good idea. For this particular problem, there's a very natural single row number evaluation metric, namely the cross-validation error. We'll see later examples where coming up with this sort of single row number evaluation metric may need a little bit more work. But as we'll see in a later video, doing so will also then let you make these decisions much more quickly of, say, whether or not to use stemming. And just as one more quick example, let's say that you're also trying to decide whether or not to distinguish between upper versus lowercase. So, is the word mom with uppercase m versus lowercase m, should that be treated as the same word or as different words? Should these be treated as the same feature or as different features? And so once again, because we're the way to evaluate our algorithm, if you try this out, if I stop distinguishing upper and lowercase, maybe I end up with 3.2% error, and I find that therefore this does worse than if I use only stemming, and so this lets me very quickly decide to go ahead and to distinguish or to not distinguish between upper and lowercase. So when you're developing a learning algorithm, very often you'll be trying out lots of new ideas and lots of new versions of your learning algorithm. If every time you try out a new idea, if you end up manually examining a bunch of examples again to see if it got better or worse, that's going to make it really hard to make decisions on do you use stemming or not, do you distinguish upper and lowercase or not. But by having a single row number evaluation metric, you can then just look and see, did the error go up or go down? And you can use that to much more rapidly try out new ideas and almost right away tell if your new idea has improved or worsened the performance of the learning algorithm. And this will let you often make much faster progress. So the strongly recommended way to do error analysis is on the cross-validation set rather than the test set, but there are people that will do this on the test set, even though that's definitely a less mathematically appropriate, so the less recommended thing to do than to do error analysis on your cross-validation set. So to wrap up this video, when starting on a new machine learning problem, what I almost always recommend is to implement a quick and dirty implementation of your learning algorithm. And I've almost never seen anyone spend too little time on this quick and dirty implementation. I've pretty much only ever seen people spend much too much time building their first, supposedly quick and dirty implementation. So really, don't worry about it being too quick, or don't worry about it being too dirty, but really implement something as quickly as you can. And once you have the initial implementation, this is then a powerful tool for deciding where to spend your time next, because first you can look at the errors it makes and do this sort of error analysis to see what mistakes it makes and use that to inspire further development. And second, assuming your quick and dirty implementation incorporated a single row number evaluation metric, this can then be a vehicle for you to try out different ideas and quickly see if the different ideas you're trying out are improving the performance of your algorithm, and therefore let you maybe much more quickly make decisions about what things to fold in or what things to incorporate into your learning algorithm.